Hello students, welcome to part 3 of the chapter, Some Basic Concepts of Chemistry. In this part, we are going to see about laws of chemical combination. In the last part, we saw matter and classification based on its physical state as well as in macroscopic level. So here we are going to see laws of chemical combination, and all these laws of chemical combination were the aim was to discuss or to explain how elements in the last part we saw what are elements and how are they classified. So elements are nothing but they are pure substances that has only one type of atom in it, so they are called elements. And compounds are pure substances that are formed or that contains more than one type of atom. So in this part we are going to discuss about laws of chemical combination, and here we discuss how these elements, which are pure substances, combine to get compounds that contains different elements in it or different atoms in it. So this is what the basic laws of this chemical combination implies. So there were 5 different laws, and the first one to that is law of conservation of mass, and it was put forward by Antoine Lavoisier. And the second law is law of definite proportion, or it's also called law of definite composition or constant composition, and it was put forward by Joseph Proust. We will see all these laws one by one in the coming slides. And 5, that means the third out of 5 law, fifth law is that the third law is law of multiple proportion, put forward by John Dalton. And the fifth law or the fourth law is Gay-Lussac's law of gaseous volume, put forward by Gay-Lussac. And finally the fifth one is the Avogadros Law, put forward by the Italian scientist Avogadro. So these are the 5 laws that we are going to deal with in this part. So let's straight away go to the law of conservation of mass. So one thing you have to remember, that every law is about how elements combine to form compounds. So that's given here, how the different elements combine to give compounds. So the first law is law of conservation of mass, put forward by Antoine Lavoisier, who is a French chemist who lived in the 18th century, end of 18th century. And he lived during the time of French Revolution, which you might have learned about French Revolution in your social studies in the history part in class 10 or 9. And he was murdered during the time of French Revolution. So before his death, he has contributed immensely to the chemical laws. So what he observed was, when elements combine to form compounds, they are just changing its form or shape, its form and shape, only that. Nothing is lost. Whatever you have here as the reactants, you will get that here as the compounds. So with all the latest knowledge what we have, we feel like it is very simple, but during his time it was not that simple. So he did some experiments and he proposed that during a chemical combination, whatever you give as reactants, as mass, you will get the entire mass as products. So only thing what happens in between is transformation. Energy means matter will be transformed from one form, that is reactants, to products. There is no destruction of matter. There is no laws of matter. This is what he said, laws of mass or laws of matter. This is what he proposed as a law. So law of conservation of mass. So it will change its form, but mass remains unchanged. So that means mass of reactants will be equal to the mass of products. Whatever mass you lose from the reactant side, it will be formed in the product side. Or it can be named as law of conservation of mass in a way that matter can neither be created nor destroyed, but can be changed from one form to another. So this is the law. If you ask to state the law is like this: matter can neither be created nor destroyed, but can be changed from one form to another. So this is the first law of conservation of mass, put forward by Antoine Lavoisier. Going to the second law, again a French chemist who lived at the same time, uh, but he survived French Revolution. He lived in France itself, and his name is Joseph Proust. So he said that he found that he was studying in compound that was formed from copper, carbon, and oxygen, and the compound was cupric carbonate, CuCO3, cupric carbonate, and he found that he found cupric carbonate from nature, and also he was able to synthesize cupric carbonate in the laboratory, so synthetic methods. In both cases, he found that cupric carbonate has always the same element, always the same elements combined in the same ratio of their mass. As we know that copper carbonate, now we know its formula, CuCO3, and if you look into the mass of each their masses are fixed. During his time, it wasn't that known. It was not that they thought that even though the compound is the same, there may be a difference in the proportion, but he said that it is not like that. Cupric carbonate, regardless of its source, regardless of his method of synthesis, always had the same. So let's look into the proportion. So mass of copper is 51.35, so its percentage. Carbon percentage is 9.75, and oxygen, so out of 100 grams, so always from wherever the source it is coming, always copper possess 51.3 percentage of the mass of this compound, 9.75 percentage of carbon in this compound, and oxygen possess 38.9 percentage of mass of this compound. So this is what he said. And today we know that, for example, carbon dioxide can come from various sources. Our respiration, as a part of pollution, as a part of lightning. Carbon dioxide can as part of fire. All these things, carbon dioxide come out regardless of the source. Carbon dioxide is always having carbon and oxygen, which has a fixed mass. This we know. This is what he stated. So in his statement, he said that law of definite proportional composition by mass, a given compound, this is the definition for this law, statement of this law: a given compound always contain exactly the same proportion of elements by weight. So a given compound always contain exactly the same proportion of elements by weight. So if you look into the credibility of these laws, for example, the first law of conservation of mass, it has been seen that there are exemptions. In some cases, it is not always conserved, especially if you look into the Einstein's equation, E is equal to mc square, where mass can be converted into energy. So if that is the case, then that law will be violated. So in most cases, that law holds good, but in many cases, in some cases at least, the laws just violate. Similar is the case with the law of definite proportion. Here, Joseph Proust says that a given compound always contains exactly the same proportion of elements by weight. But later it has been discovered that in certain compounds, it is not always the same. There are sometimes such compounds are called non-stoichiometric compounds. For example, there are still more compounds, but it does not hold always good. In some cases, it violates. But during those days, and it has laid some foundations for the chemist to do further research. So this is the law. And law of multiple proportion, put forward by John Dalton. You might have learned about him in the lower classes, that he is the one who put forward the atomic theory and the postulates leading to the atomic theory. So it is John Dalton who put forward the multiple proportions. So let's look into an example what he did. So we know that N2 and O2 are elements, and it can form nitric oxide, which is a pollutant, and also it can form nitrogen dioxide, which is another pollutant in the air. So nitrogen and oxygen can combine and form two pollutants, nitric oxide and nitrogen dioxide. If you look into these compounds, you will see that one of the atoms has a fixed mass. Here nitric oxide and nitrogen dioxide have the same mass of nitrogen because it's having the same number of hydrogen, whereas what is varying is the number of oxygen, or its mass is doubled. Here if it is 16 grams, here it is 32 grams of oxygen, or you can say 32 atomic mass. Here it is 16 atomic mass. So using this observation, John Dalton, not only this, based on many other like carbon monoxide and carbon dioxide formed from carbon and oxygen, have this similar case. Carbon is the same in both, but oxygen is doubled. So we can take enormous examples. By looking into these examples, John Dalton tried to put forward a law. So that's what in nitric oxide we have 14:16, it's their atomic mass, whereas in the case of nitrogen dioxide it is 14:32. So using this, he's tried to figure out a ratio between the varying masses. What is the varying mass here? Oxygen is the varying mass, nitrogen is fixed mass. So he tried to compare the ratio between the varying masses. Varying masses is, here it is 16 gram and here it is 32, and he tried to figure out the ratio. It is 16:32, and he simplified the ratio and he put a law based on this. What does a law says? If two elements combine to form more than one compound, if two elements combine to form more than one compound, here you can see two elements, nitrogen and oxygen, combines to form more than one compound. The ratio of masses of one element, which element we have taken here? It's oxygen, that combines with fixed mass of another element. So which is the fixed mass? That is nitrogen. So varying mass is oxygen, so their ratio are small whole numbers. Is it so here? Yes, if you simplify it, you will get this simple or small whole number ratio. So this is what John Dalton tried to put. He said that elements can combine more than one compound. So if one part is fixed, the other part will be varying, and that varying part have a ratio between them in a small whole number. So this is what he put, and later it was found that it is not always true, because there were certain compounds called organic compounds that can have large or big whole number ratios. 1:, like that, 1:, more than 100. So some ratios are like that in the case of organic compounds. So at least many of the inorganic compounds hold good in the case of Dalton's law of multiple proportion. So what was law of constant proportion? Constant proportion, you should identify from that name itself. It says that regardless of the source, always their ratio is constant. Elements masses ratio is constant. Whereas what is multiple proportion? The same elements will give multiple products, and the ratio between these multiple compounds, or the elements or the atoms in that compounds, bears a simple whole number. So that's the difference between law of constant proportion and law of multiple proportion. The fourth law, Gay-Lussac's law of gaseous volume. If you are looking into this law put forward by Gay-Lussac, again another French scientist who lived again during the same era of, so he was bit young when all these other French scientists were in the field. So he put forward based on gaseous reactants and products. So if there are two elements, for example H2 and O2, giving H2O, so he treated them all as gases. So he treated hydrogen gas with oxygen gas, and he was able to produce water gas, or can say water vapor. And he said that he tried to balance them. So he said that there are 2 hydrogen plus 1 oxygen giving 2 water molecule, 2 hydrogen plus 2 oxygen giving 2 water molecule, and he tried to evaluate the ratio of their combining volumes. So if you take 2 volumes of hydrogen and 1 volume of oxygen, you are getting 2 volumes of water. So he laid down the law like this. So if you take 2 volumes, here the volume is in liter, so if you take 2 liter of water plus 1 liter of oxygen, you will get 2 liters. So this is the balanced equation. This is one such information that you will get from a balanced equation. You can combine the volumes of the reactants and products. You can not combine, you can compare the volumes of reactants and products. So if this in this balanced equation you have 2, that means you can say that 2 liter of hydrogen combines exactly with 1 liter of oxygen. If they combine in the exact way, you will get exactly 2 liter of water. This is what you get from a balanced equation, which you will learn again about this information that you can gather from a balanced equation later in this chapter. So coming back to this law, it states that 2 liter of hydrogen plus 1 liter of oxygen giving 2 liter of water. So he, based on this information, he laid down, he tried to figure out the ratio of volumes of the reactant gases and the gaseous product is in simple whole number. So what is the ratio here? 2:1:2. So this is what he figured out. Ratio of volumes of reactant gases and products is in simple whole number. Then he put down the law. According to the Gay-Lussac's law, when gases combine or are produced or are producing products in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at same temperature and pressure. So temperature and pressure must remain the same. If there is any difference, volume will change. So that whole number ratio will go. Clear? So Gay-Lussac's concentrated on gaseous systems, the reactants and products when they are in gaseous state. So you can see it from here. You can see that it's written, it's gas, oxygen is gas and water is gas. So when they are in gaseous state, they are combining volumes. Their volumes actually are of simple whole number ratios. Funny part of it is that during his time, that the hydrogen that we write here is not known as diatomic atom, diatomic molecule. Diatomic molecule means a molecule has 2 atoms of hydrogen. However, the structure or the molecular formula of water is known, but molecular formula of oxygen and hydrogen was not known. So they thought that hydrogen was a sphere like an atom, oxygen was a sphere like an atom, nitrogen also was like a sphere. So they never thought that a molecule of hydrogen will be a combination of 2 atoms. This was first proved by Avogadro, who has explained the next law. So Avogadro's law. Avogadro was an Italian, and he too lived in the same end of 18th century and beginning of the 19th century. So he said that 1 liter container, if 1 liter container that is in 1 bar pressure and 25 degrees centigrade, so you have the temperature and pressure. If this 1 liter container has X number of hydrogen molecules, if this 1 liter container at this temperature and at this pressure has X number of hydrogen molecule, then 1 liter container that is at the same temperature and same pressure and having same volume will contain X number of air molecules. So then he noticed this, and then he laid down the law. What is this law? Equal volumes. So here you have the equal volume, right, of all gases at same temperature and pressure. You have the same temperature and pressure contain equal number of molecules. So here it is hydrogen. So if this hydrogen is having X number of molecules in same volume, same temperature and same pressure, then any container that is at same temperature, pressure and volume will have same number of molecules of any gas. Clear? Here it is air. Now if you are taking oxygen, if it is having same pressure, temperature and same volume, you just try to count out the number of oxygen molecules. It will be the same. So this is what Avogadro said. According to Avogadro law, can make it very easy and very fast. Equal volumes of all gases at same temperature and pressure contain equal number of molecules. Equal volumes of all gases at same temperature and pressure contain equal number of molecules. So if it is a room, if that room has same temperature and pressure compared to the another room and having the same volume, then for sure the number of molecules in that room and the number of molecules in the other room will be the same. Doesn't matter the gas is X or Y. How big the molecule is doesn't matter. Number will be always the same if the volume, temperature and pressure is the same. This is what Avogadro said, and it was true. But during that time, it was the period of Dalton, John Dalton, who was one of the famous scientists during those days, but nobody noticed about this law and got little importance. But after his death, another scientist called Canizar, who was working with organic chemistry, put forward his findings, or Avogadro's highlighted Avogadro's findings, and which got attention, and this has changed the chemistry's viewpoint. Let's see how Avogadro's law helped to identify hydrogen, oxygen, nitrogen as diatomic molecules. Until Avogadro, everyone thought that hydrogen means it's an atom, oxygen means it is an atom, nitrogen means an atom. But after Avogadro's law, after the recognition, everybody realized that it is no more an atom but an molecule to hydrogen atoms. So using his own law, Avogadro established that gas molecules can be diatomic, like H2, O2, N2, etc. How? Let's see. So all the scientists believed that gases are atomic in nature, like hydrogen is like an atom, oxygen is like an nitrogen, etc. So if it was atom, Gay-Lussac's did this experiment. 2 liter of hydrogen plus 1 liter of oxygen gave 2 liter of water. This is what Gay-Lussac did. 2 liter of hydrogen plus 1 liter of oxygen gave 2 liter of water. So according to this is Gay-Lussac's law. According to Avogadro's law, what was it? 2H plus 1O giving 2H2O. 2H plus 1O giving 2H2O. So if this has to be happened, so what will be that? Let's see. If hydrogen and oxygen were atoms, if hydrogen and oxygen were atoms, what will happen? Let's see. According to this, we have 2 hydrogen atoms, 1 oxygen atom. If they combine, we have only 2 hydrogen atoms, we have only 1 oxygen atom. If they were atoms, like what John Dalton believed, or his contemporary scientists believed, if it was like that, then 2 hydrogen atoms will combine with 1 oxygen atom to give only 1 water molecule. But what Gay-Lussac saw was there was actually 2 water molecule. So in order to get 2 water molecule, there is only one way. There is only one way for that. So this is not working. This is not what Gay-Lussac saw, and there is only one way if they are H2 and O2 respectively. So let's take the same figure here. We have 2 atoms of hydrogen, oxygen, and to get 2 molecules, that means that here oxygen must be a molecule. So now it's satisfied. And to get 4 hydrogen atoms here, there should be 4 hydrogen atoms, and for that it should be diatomic molecule. Clear? I guess it's clear. So if it was atoms, then Gay-Lussac will see only 1 water molecule, but he saw 2 water molecules. You can see if it was treated as atoms, he might have got only 1 molecule, but he got 2 molecules. To get 2 molecules, both oxygen and hydrogen must be diatomic. There is no other combination possible. And from this, Avogadro concluded that all the gas molecules which are elemental form like hydrogen, oxygen, nitrogen, chlorine, fluorine are all diatomic. There are even compounds which are not diatomic, but he proposed that such atoms or such molecules, H2 is diatomic, diatomic means 2 atoms, oxygen is diatomic, nitrogen is diatomic, etc. But during his time, when big scientists were there, they were not ready to accept it. But later, after his death, after Avogadros' death, one of the famous scientists called Cannizzaro brought this law up and said that he has something to prove, and he showed this and everybody started believing, and Avogadro has changed the science or the concept of chemistry from there on. So this is the true part of it. This is the right way. So if you're looking into, again based on this Avogadros law, let's look into an example. If 1 liter of A and 4 liter of B is mixed in a vessel, imagine that they will not react. A and B are non-reactive, and I mixed 1 liter of A and 4 liter of B in a vessel. What will be the volume of the resulting vessel if temperature and pressure remains the same before and after mixing? So I am not changing temperature and pressure. I just mixed 1 liter of A and 4 liter of B, so that the vessel is flexible to move, so that the pressure must be the same. What will be that? They are non-reactive. That means the resulting volume will be 5 liters. Clear? According to the Avogadros law. Let's try to understand this with another one. So A and B are two reactive gases. A plus B giving AB. Clear? Imagine that 1 liter of A is mixed with 4 liter of B. 1 liter of A is mixed with 4 liter of B in a vessel at 1 atmosphere and 0 degrees centigrade. What will be the volume of the resulting vessel if the temperature and pressure remains the same? So I am not changing the temperature and pressure. It remains the same after the reaction. And the point is, A will react with B, and I mixed 1 liter of A and 4 liter of B. If you look into the balanced equation here, you will see that 1A will react with 1B to form AB. So you have 1 liter of A and 4 liter of B. So in 1 liter of A, if there is a number of molecules inside it, same 4 liter will have 4 times of A. So 4 times of A. So B will be having 4 times A based on the Avogadros law. In this, 1 liter of A reacts with 1 liter of B from here, isn't it? So this will react to form 1 liter of AB. That means that 1 liter from B and 1 liter of A has now reduced to 1 liter. So from here 1 liter and here 1 liter, they will react. So these 2 liters, 1 liter from A and 1 liter from B, will now reduce to 1 liter. What is remaining in B? Remaining in B is 3 liter unreacted one. So 1 liter AB and 3 liter of unreacted B. 1 liter of A reacts with 1 liter of B to give 1 liter of AB. Now what is left over? In container there will be 3 liter of unreacted B. So 1 liter of AB and 3 liter of unreacted of B will give total of 4 liter. So 1 liter of AB and 3 liter of B, the total volume of the reacting vessel or the gas that is inside the vessel will be 4 liters. So I hope you have enjoyed this laws of chemical combination. If you have any doubts, please go through it again. Thank you.